Okay, so lesson 1.6, curved paths. So we are going to be talking about, two-dimensional motion, right? So we've got two-dimensional motion, and we've looked at one-dimensional motion, whether we go left or right, up or down. We've talked about two-dimensional motion, like in projectile motion, where we're doing left and right and up and down at the same time. The third type we need to talk about is circular motion. It really is still technically two-dimensional motion, but it's a constantly changing two-dimensional motion. All right? So, some of the things we have to look at, and let's look at this. When we talk about curved path, because this is exactly what we're talking about. We're talking about something going in a circle. That is a curved path, isn't it? Okay? So what does that look like? We've got two types of acceleration happening, okay? And what do we see that? We have a perpendicular, which is called a normal one to the path. That would be this guy. Let me find it. Sorry, so the acceleration itself, the acceleration itself is going to be going this way. When we look at that, we have one that is going sort of parallel to the path at that point. That's going to be tangent. So this is our parallel one, the one that is tangent to it. In other words, it's going to be in the same direction as the velocity. And then we've got an acceleration that is going perpendicular to that path. And the path perpendicular is going to be this direction. So this is a perpendicular. When you put those two things together, you get this guy right here, right? Because this is going to be at 90 degrees to each other. All right, so how do we know? When the acceleration is parallel to the path of the motion, and remember we said that's this guy in blue, parallel, the one that's going in the same direction as the velocity, okay, that's the one that acts to change the speed because it's going in the same direction as velocity. So this is going to be our tangential acceleration, all right? Now, that's the one that changes the speed. However, the one in red, which is the one that is, if you remember, normal or perpendicular to the velocity, that's the one that is changing the direction, okay? Think about it. The one going in, if it's going in a constant velocity, you don't really have an acceleration that's changing it in that tangential direction. What you have is it's really changing direction most of the time. As it goes around in a circle, it's going this way, now it's going this way, now it's going this way, now it's going this way, and so on. Even if it's going at a constant velocity, we don't really say that it's still not a vector. It does, in a circular case, still have acceleration. All right, so this is going to be what we call our radial acceleration. So radial is the one that changes direction, and tangential is the one that changes the velocity, okay? So keep those in mind as we do this. All right, so now let's talk circular motion. All right, so when we have an average or an instantaneous velocity, if we're looking at circular motion, we're talking about motion with a constant perpendicular component to acceleration. All right, so the magnitude of centripetal acceleration. Now, the centripetal acceleration is going to be the acceleration that acts in towards the center of the circle. So centripetal acceleration is this guy right here. This is a centripetal, okay? So we've got centripetal acceleration acting towards the center of the circle. So this is going to be our radial. So centripetal is going to be our radial. All right. Now, if you remember, most of you, we call this A sub C, and this is going to be V squared divided by R. This was a physics 1 thing. So Sam, this is going to be new to you. Okay, it only acts to change the direction of the velocity. Okay, it keeps the object, this is the one that keeps the object going in a circle. Okay, if you didn't have this, if the centripetal or the radial acceleration went away, then what you would have is this object flying out of the circle and going straight tangent to whatever the arc was at that point. So if you cut off the radial, then all you have is what? Means you only have tangential, and this thing that was moving in a circle suddenly just keeps going. So it had radial acceleration, and now it has no centripetal acceleration, okay? So it just keeps going. All right. So now, answer the question for me. By the way, this is also why if you were on a ride that goes in a circle, you remember those, some of you have been to the fair, or some of you have been to like Six Flags, where they have the one that they stick you in. I think they've actually got one at the Space and Rocket Center too, where they put you on the side of the wall and they spin it really, really fast, and then they drop the floor out, but you still stick to the wall. That's because of reaction to radial acceleration, okay? Radial acceleration, remember, you've got an acceleration coming in, you also have a normal force as a reaction to that, right? And so what we call that, the reaction, is what we call centrifugal force. It is an imaginary force, okay? But it's the one that presses you back. So if an acceleration exists in a uniform circular motion, then why do objects move at a constant speed? The reason they move at a constant speed is because A, tangential, uniform circular motion, A tangential doesn't exist. In other words, A sub t is equal to 0. However, A centripetal does. So it moves in a circle, right? So now, what if the speed is not constant? So if the speed is not constant, then it must have a tangential component. So if something is moving in a circle, it never, even if it's at a constant velocity, it never has no acceleration. So let's look at example B here. A car has a constant acceleration of 0.3 meters per second squared, parallel to the roadway. So it's telling us it has a constant acceleration. The car passes over a rise. Because it passes over a rise, we can assume that this is part of a much bigger circle, right? Which means that we are going to have a centripetal also, all right? Shaped like an arc, and that circle has a radius of 500 meters. Notice that A sub c is v squared divided by r, which is the radius of the circle it's part of. So that's going to be the radius of that arc. At the moment the car is at the top of the rise, its velocity vector is horizontal. So it's telling you it has a velocity this way of 6 meters per second. What's the magnitude and direction of the total acceleration? So for total acceleration, we are going to need to find v tangential and v centripetal, or v radial, if you want to think about it that way. So how do we do that? So for v tangential, v, a, we're going to find a tangential and a radial, which of course is a centripetal. So let's find those. Let's find a centripetal, which is going to be v squared over r. Well, what is v? Gives me 6. So this is going to be 6 squared divided by what? 500. So 6 squared divided by 500 is 0.072 meters per second squared. So that's that. A tangential tells me that there's an acceleration parallel to the roadway. So parallel to the roadway tells me this is my A tangential. So this is 0.300 meters per second squared. So if I want to find the entire total acceleration, which would be this, that's going to be, of course, there's that relationship that right here, which this is A, and this is what? A tangential, and this is A radial. So it's Pythagorean. So we're going to have a centripetal squared plus a tangential squared. So we just plug in 0.3 squared plus 0.072 squared. Take the square root, we get 0.31 meters per second squared is our total acceleration. Okay? All right, so now, when we talk about something going around in a circle, period is a good thing to talk about. The time for going around one period is capital T. It's that weird looking T. It, of course, is going to be your distance. It's going to be your distance around the circle, which, of course, is divided by your speed. So that is going to be circumference divided by velocity. So this is going to be 2 pi r divided by v. Okay? Frequency, of course, is the number of revolutions per second, and it turns out that frequency, if you remember from pre-cal, is 1 over the period. So that turns out to be v over 2 pi r. Okay? All right. Which, if we want to put in terms of velocity, we now know that velocity is equal to frequency times 2 pi r, if we just cross multiply here. Units for frequency are going to be hertz. Hertz, which are 1 unit per second, which is seconds to the negative 1. Period, of course, being its units are in time. Its units are seconds. Okay? So let's look at C. Suppose a space probe withstands a stress of 20 g acceleration. That's pretty cool. The craft is moving at the speed of 1/10 the speed of light, so it gives us a velocity. How long would it take to complete a 90-degree turn? That's a quarter of a circle. So the first thing we need to figure out is what the centripetal force is. The centripetal force, they're giving us the stress of g's, so it's going in a circle. So a centripetal is going to be 20 g's, which of course is 20 times 9.81. So if we do that, 20 times 9.81, let me go grab a calculator here. $196.2 meters per second squared. All right. That is equal to what? V squared over r. So a centripetal, which is equal to v squared over r. We know we can fill in 196.2 is equal to the velocity, which is 3 times 10 to the 8th times 1/10 divided by r. So now we're going to find r. Now, why do we want to find r? Oh, and this is squared because it's v squared. So what do we get for r? We want to find r because we want to know how far it is around the circle, right? How long it would take is we need to know the radius of the circle. We need to know how far it's going to go before we figure out how long it's going to take. So 3 to the 8th power divided by 10, go square that, get that. I want to we get about 4.5 times 10 to the 12th meters, 4.59. So if we have that, now we can figure out what the time is. Okay, so we want to know if we're going, we want to know the period. Time would be the period, right? The period is 2 pi r over v, but we only want to go a quarter of the way, don't we? So we're going to multiply that by 0.25. Okay? So we can do that, can't we? So let's figure it out. 2 pi times 4.59 times 10 to the 12th times 0.25 divided by the velocity, which we said was 3 times 10 to the 8th, 1/10 of that. And we can get the time. So let's figure out how much time that is in seconds. I get 240,331.838 seconds, but I don't really want that in seconds because that's ridiculous. So I need to change that to hours, don't I? And so I'm going to divide that by 3,600, and I get about 66.8 hours. So that's the period to go a quarter of a circle. Okay, so let's look at example D. A particle has a position given by r, and it gives it to us in cosine and sine. That's cool. Find the equation of the object's linear motion. So we know the equation of a circle is x squared plus y squared equals r squared, don't we? We learned that in pre-cal. That is a equation of a circle. So we know what r is. So all we have to really do is what? X squared plus y squared is equal to the I component and the squared and the j component squared. So r cosine omega t squared plus r sine omega t squared. If we pull that out, we get r squared cosine squared plus sine squared, which is 1, isn't it? So we do get x squared plus y squared equals r squared. That's pretty cool. So now, we knew that because it's a circle, okay? So now, how do we find the next piece of this, which is find what? Find the acceleration, okay? So to find the acceleration, we know that first thing we know is we know x of t, well really r of t, is going to be the radial motion, isn't it? So r of t, which we know is sine omega t, actually, excuse me, it is what? Yeah. Cosine plus sine, okay? So cosine omega t in the I hat direction plus sine omega t in the j hat direction. So that's r. So now we need to do velocity, which is the derivative, right? dr dt, which is going to be what? Oh, I forgot my r in front of each one, didn't I? R and r. All right, so now what? So dr dt is going to be we're going to take the derivative of cosine, so that would be negative r omega sine omega t in the I hat direction plus r omega cosine omega t in the j hat direction. Then to find acceleration, I just take the derivative of dv dt. So again, that's going to now be what? Negative r omega squared cosine omega t in the I hat direction plus negative r omega squared sine omega t in the j hat direction. I'm just taking the derivative of both of them, okay? So there's my acceleration. Now it says, what's the linear acceleration? Well, the linear acceleration is going to be what? The absolute value of a sub t. All right, which means that we're going to have to take and square the x component and the y component and add them together. So negative r omega squared cosine omega t squared plus negative r omega squared sine omega t, sine omega t squared, take the square root of that. So if we do that, what do we get? We get r squared omega to the fourth cosine squared plus r squared omega to the fourth sine squared omega t. You can see where this is going. Square root of r squared omega to the fourth, if we pull out cosine squared plus sine squared, that goes to 1, so it disappears. So the linear acceleration is going to be square root of r squared omega to the fourth, which is just r omega squared. Well, omega is v over r. So this is r, v over r squared. This is omega. So we get r v squared over r squared, which is v squared over r, which turns out is what? That's the centripetal acceleration, isn't it? So you've just derived centripetal acceleration from the motion of a circular object, okay? And that's it for the notes from here. You do need to know how to do this. You need to go back through and watch very carefully what the derivations are. You need to know how to derive something using from the position, even if it's not just a plano position, but it's a circular position, and keep going with it. All right.